Good afternoon, everybody. Welcome to the second live session of this NPTEL course, Transition Metal Organometallic Chemistry from Principles to Applications. So it's been about 40 lectures or so have been given in this particular topic. And as usual in this live session, we're going to be discussing if any questions or queries that you may have regarding the content which is covered. So I request you to send your comments and queries via chat box given on the bottom right of your screen, and we'll answer them in the order in which we receive. Good afternoon once again. So this is the live interactive session for the NPTEL course Transition Metal Organometallic Chemistry from Principles to Applications. So I request you to send us your query in the chat box, and we'll answer them in the sequence in which we receive them. Good afternoon, Arubi. Arubi, I got your email, and I would be happy to host you, provided you're eligible for the fellowship internship. And I think the best thing would be that you write directly to the NPTEL, and uh, if you're eligible and if you're offered, then you can come over. However, the accommodation has to be taken care on the part of the NPTEL or at the individual level by at your end. Okay. You know, Wittig reaction per se is kind of similar to what we know about olefin metathesis, where it is a carbon transfer reagent reaction where the uh, the, uh, the CH2 moiety is transferred from over the phosphonium elect in the Wittig reaction case uh, to a carbonyl compound in case of Wittig reaction, whereas the same parallel can be drawn with respect to metathesis, where the carbonic moiety bound to the metal gets transferred over to another olefin. Uh, so it's sort of like uh, can be seen as something which is proceeding by a similar mechanism. Is there anything else that you want to ask? Did I answer your query? Welcome to this live interactive session for the NPTEL course Transition Metal Organometallic Chemistry from Principles to Applications. I request uh, the students who are taking this course and who are uh, connected to us at this moment through this live session, if you have any comments or queries, you are requested to sending your comments or queries through the chat box, and we will answer them in the order in which we receive. Can you instead of giving the time, can you be more specific about what questions you have? Instead of saying what time, because at that time there will be several slides that may be referred to, but it would help if you tell us the questions that you have, and if you want to know about the content is already there in the slide. I request you, see, Orve, it's not going to be a rerun of the lecture which is given out there. Uh, can you just specifically ask questions that you may have? We're not going to again say the same thing which is there. Please be specific in asking questions or queries as per your slides. Now, so there was a pi acidity topic discussion which was discussed around at that time for making carbene carbene complexes from carbene using BF3 or Lewis acid, boron-based Lewis acid. And that was the way Fischer carbine was made, metal carbon triple bond. And that was achieved by using Lewis acid. But it's difficult for me right now to understand whether you are referring to that particular thing or in general you're asking about what is pi acidity or pi basicity. It would be helpful if you come up with questions, like exact questions that you may have, and we'll answer them in the order in which we receive them. Okay, thank you. Uh, Welcome to this second interactive session of this NPTEL course, Transition Metal Organometallic Chemistry from Principles to Applications. I request the students who are attending this live session to type in any queries or questions they may have, and we'll be happy to answer them. Now, please type in your questions in the chat box given on the uh, bottom right corner of your screen. See, in general, if you look at this concept, basicity, pi basicity, sigma basicity, if a lone pair, which is there in the sigma bonded orbital uh, in a ligand, if it donates that lone pair to a metal cation and cation binds to it, it is a sigma donation of the ligand is uh, sigma bonded to this. Now, if there are pi electrons and then uh, the pi electrons are engaged in binding to metal, like olefin getting bound to metal in a Zeiss complex. That is also a sigma donation, quantitative donation from a pi thing, pi electrons. Now, if a ligand uh, uh, accepts electron instead of, usually what is the property of ligand? The property of ligand is basic in nature. They have a lot of electron density and they ended up donating electron to the metal, and that's where the basicity of ligands stems from. But if in case a ligand is able to accept electron, uh, uh, then it becomes acidic. Now, usually in carbon monoxide, what we see that the CO can accept electron from metal d orbital, and that's why it becomes pi acidic. Now, this electron which carbon monoxide pi orbital accepts, actually that accepts in the pi antibonding orbital. So that's how the stem of pi acidity arises from. Uh, Conventionally, what we see is that all ligands are electron-rich entities. They can be electron-rich neutral species or electron-rich anionic species, whereas all metals can be electron-deficient cationic species. Uh, and the flow of electron usually happens from the electron-rich entities to electron-deficient entities. So it's like basicity on the part of the ligand and acidity on the part of the metal. But in transition metal, what we see that after the first donation happens, that the sigma bond has happened, there can be back donation from the metal d orbital onto back to the ligand. And they are for certain specific ligands like carbon monoxide, where they can accept electrons into the pi star antibonding orbitals. So not all of them, but some of them, like carbon monoxide and all. So those ligands are pi acidic in nature. That's how the term pi acidity sort of came in being. And primarily, pi acidity is more associated with that of CO kind of ligand. So welcome to this second live interactive session of this NPTEL course, Transition Metal Organometallic Chemistry. Again, I'm repeating the same thing for sake of students who might have joined in later in this session. So the idea for being in this session is that we try to take up questions and queries which a student taking this course might have, and this gives us an opportunity to answer them live. So I request people who have joined in later in this session to give their comments and queries in the chat box given in the right bottom corner of your screen, and we will answer them in the order in which we receive them. Yeah, again, instead of giving the time of the lecture, kindly please be specific in the question that you want to ask. This is the same product. There are two pathways being highlighted. One is CC activation. This is, can you get to the slide? Another another is CH activation at a very high temperature. The CH activation relatively lower temperature. Then question is, but it leads to the same product as the CC activation. No, uh, actually, I request you to kindly look at the reactions. You will see that uh, in one case, the rhodium is bound directly to the carbon, uh, and in the other case, there is a CH2 group. Achha. Now, what you are saying is that overall it goes to the same product. Uh, but there are two things. One is the first step which happens is CH activation and CC activation. Now, CH activation happens at a lower temperature than the activation, and that is fine because uh, you know it is difficult to get to CC bond. Now, after the first reaction has happened, then a secondary reaction may happen leading to the same product, but that is not the case. Can this process of CH activation to gain end product of the single step is be used? This can this process be used for other transition metal? Uh, uh, Forget other transition metal. Can this process be used for another rhodium complex of similar different ligand? The answer is very open. It may be, it may not be, depends on the energetics of the reaction. Depends on the energetics of the reaction. So it all depends on the reaction trajectory, how all the intermediates for that specific reaction are interspaced, and then based on their relative energy and relative activation barriers, certain reaction may proceed and certain may not. The steps which are shown and the intermediate steps and the intermediates which are shown for this particular reaction is only valid uh, for this particular reaction. Now, one may extrapolate that whether this can be extrapolated for another ruthenium, iridium, iron. The answer to that is nobody knows. Unless one does the reaction, again maps out all the intermediates and trajectory and calculates all the transition states, and then whatever would be the lowest part for that particular metal, then that would be the reaction trajectory for that. So there is no general transferability of these steps from one particular reaction to another. No. That's the reason being why you cannot just directly transfer to all other metals, because all metals are different. Every metal is unique. They have their own steric and electronic requirements, and their reactivity is dependent very much on them. Similarly, different ligands has different topography, different steric demands, different electronic demands. So when a combination of a different ligand and different metal happen, then all the reaction dynamics has to be recalculated with respect to this particular metal complex and see whether these intermediate will come out as same as what has been observed for another reaction. So there is no guarantee. One has to do, and then one has to see whether it will proceed exactly the same way or other. Do you have any further questions on that? Same rhodium, if they have different ligand, uh, it may not undergo exactly similar uh, reaction types. There are set of complexes. For example, I just said that they would be different, but for a family of ligand of similar steric and similar electronic requirement, and if all of this one particular family of ligand, if they bind to metal, uh, then they may show similar type of reactivity. For example, let's say carbene-based palladium complexes. Now, when they do cross-coupling reaction, all of them show three states: oxidative addition, reductive elimination, transmetallation. So that is because of the fact that the ligand and the metal, they are of similar type. Metal is always palladium, and ligand will be something which is similar to a variant of that. And that is the reason why the cross-coupling reaction sort of show similar path. But specifically, each reaction trajectory has to be worked out for uh, uh, a particular ligand and a particular metal combination. It is sort of similar to saying on a lighter note. For example, will the two siblings of a family exactly be the same, even though they have same father, mother? Will both of them grow up to become take up the same profession and both of them exactly do the same thing? No, each one is different, and they will find their way based on their own temperament and requirement, even though they might have uh, uh, come from the same home, similar. So all these reactions, they show the path of the least resistance, which will have the minimum energy, and it depends on what is the relative energy of all the intermediates or secondary reactions happening around the metal, and whichever has the minimum uh, energy path profile, that one will be the more dominant reaction. Uh, Now, going back to your CC and CH activation, uh, the CC activation, we discussed that it requires very high temperature. That's because it's not easy to get to a CC bond. CC bonds are actually buried within inside several CH bonds. Uh, so for a metal orbital, which is let's say a vacant metal orbital, to attack a CC bonding orbital, the metal orbital has to deepin the molecule to get to that. So that activation does not happen so easily. On the other hand, let's say if you look at the molecule, organic molecule, there will be so many CH bonds, and all these CH bonds are on the surface. Uh, So for if the same metal orbital is there, the metal orbital reaching out to a CH bond is much easier because there are so many of them, and they are just on the exterior. Whereas CC bonds are fewer of them, and they are dug deep in the interior. So for a metal orbital to activate a CH bond, it is much easier than a metal orbital to activate a CC bond, which lies at the interior and also much fewer in number. So it's basically that's what guides the higher activation barrier required for CC activation as opposed to for the CH activation. and both leading to the same thing is just because there was a methane eliminated in the last product. Now, the see if you look at the last product that you are referring to, that is overall CC activation, but it did not happen during a CH activation that way. So we got a product which could have been made directly by a CC activation, but that would require higher temperature. The same product can also be made by CH activation by the lower energy route. So that doesn't mean that the product belong, let's say a product X. A product X can be obtained at a higher temperature by CC activation, but the same product X can also be obtained via a sequential steps in CH activation. So that product X is a product from both the reactions. So the product X is not exclusively belonging to CC activation. The product X can also be obtained equally by its own right and merit be obtained by CH activation. So you cannot club this end product as the product being exclusively formed from CC activation. No, it can also be formed from CH activation at lower temperature by a series of steps, and that is what has been shown. Is it complex? The following bent shape of the cycloalkene type or the strain type shown slide, the reference slide shown at 3.17. I don't know what are you meaning? Let us get, can you give me the slide number or time? Then we can get to what you are referring to. Slide. Is it complex the following the bent shape of cycloalkene type or the strain type shape? Sodium is attached to N and the benzene ring at the it is a strained molecule. Whether if you are now whether it is strained or unstrained, first of all, any molecule there will be some strain when it is bound to a metal. Any bond. Think of this: a bond when it is between two atoms, and the atoms by virtue could have been free. So whenever they are bonded, there will be strain. Even let's say pentane is also in strain, like hexane, maybe less strain, maybe this. Whether the strain guides the reaction for the two series of steps that is shown, answer is maybe. Maybe yes, maybe that option cannot be ruled out. Now, what is the amount of strain? Can it be calculated? Yes, it can be calculated computationally. It can be calculated computationally. So, the strain of the CH2 that is formed after CH activation may lead to this further reaction, and that is a possibility. But think of this. Look at the last step. The last step of the CH2 by CH, that also requires 100 degrees centigrade. So if something is strained, and if the strain is facilitating the CC, that whatever you are referring to as CC bond formation product, obviously then it wouldn't be requiring 100 degrees centigrade to achieve the last step. So it may be strained, but it's not only the strain, or it is the strain which is guiding it. The activation energy is required, and it has to be supplied thermally. And that product, whatever you referring to as CC product, that can also be referred to as CH product, CH activation product, because the same thing can be made through CH activation. It's sort of like, let's say, if you're going to go to a city, Bombay, you can come by train, you can come by plane also. So reaching Bombay cannot be exclusively by train or any mode of transport. It can be the same city you can reach, whether you take a airplane or you take a bus, or you can walk also, you can take a bicycle also. So similarly, the same product can be reached via CC activation and as well as via CH activation, but the product does not belong exclusively to any one of the pathway. The way city of Bombay, accessibility cannot be exclusively to only one mode of transport. I think I've drawn an analogy over here. For what? No, what is the reference we want to give? It is already given. Do you have any more comments or questions? So the point to note is twofold, that the product X, whatever that product is, that can be formed via CC activation or via CH activation. CC activation obviously requires higher temperature. CH activation requires lower temperature but more number of steps. The product does not exclusively belong to any one of the formation pathways. Like the way, let's say, if I want to come to Bombay, the city cannot dictate that Bombay is only reachable by plane. We can come to Bombay by walking also. So similarly, a product can be synthesized by any of the method. Maybe a flight will take lesser time and walking will take longer time. Similarly, CC activation will take higher temperature to make the product. CH activation will take longer time, say more steps, but lower temperature. But the product by itself is accessible by both pathways, and this product cannot be exclusively attached to only one of the pathways. It is a product of both the pathways. Similarly, another analogy I'm giving, let's say you are friends with one person and you are friends with another person. Then the person A may call you friend and person B may call you friend also, but you may not be a common friend to both. But you as an individual, you are separately friend of A and you are separately friend of B, but you are not exclusively friend of A and the friend of, you cannot be friend of B. That is not there. Similar thing, no? So welcome to this again. For people who have joined in late, I request you to send in your queries and comments, and we'll try to answer them. We still have about 10 minutes, or how long? 20 minutes. We still have about 20 minutes left for this session. So again, for people who have joined in, welcome to this second live interactive session of the organometallic transition metal chemistry course. We are at about 2/3, I believe, of the whole course, and one third is still remaining. That so we are, I think, at the end of around 40th lecture or so. 20 more lectures are to go. So if you have any comments and queries and questions, we request you to kindly put it in the chat box, and we'll answer that in the order in which received. This actually is a very nice opportunity where we can uh, connect to each other. Like this being a NPTEL course, most of the lectures are given online in a video mode, so we don't get to interact. So these sessions are really very unique and useful from not only for you as a student, but also me as an instructor for this course, so that we can really talk to each other, which we miss during which we miss in an offline online uh, course than what we have in a offline session where we can discuss and debate. Uh, so please take this opportunity. If you have any comments and queries, you're welcome to put them in the chat box, and we'll try to answer them in the order in which we receive. We have had some very good, interesting questions come in this session, and we try to answer them hopefully to the students' satisfaction. So I request students, if you have any question, please type in. So again, please send us your queries if you have any. We still have about, I think, 10 minutes or so remaining. Yes, there will be, I believe, one more session is due, and that the TA involved in the NPTEL office, they'll coordinate. Yes, I believe since we are in two-thirds of the course, there should be one more session of interactive due before the course expires. I don't know when it will be done. That will be done in coordination with the TAs and the NPTEL office over here in IIT Bombay. Thank you. Yes, Urvi, it was nice uh, uh, answering your queries. These questions are good, and uh, and this is what this interactive session is about. Uh, Hopefully, at some point, you can visit us. Uh, the way you have written, you kindly contact the NPTEL office regarding the procedure, and if you're eligible, I would love to host you in our laboratory for the internship, provided you are eligible and you qualify all the requirements as per the NPTEL guideline and procedure. Also, the accommodation has to be arranged from either NPTEL's end or your end, because that's something that has to be worked out before a student comes over here. And housing scenario in IIT Bombay is quite difficult in the sense that there are so many students. So one has to take care of that. That has to be arranged prior to any student coming in the laboratory. So, but I think all of these fellowship will come with the accommodation, or they should have some provisions for accommodation. The best thing would be to contact the NPTEL office, and they would guide you provided you are eligible. Yeah, if you are interested, you should see organometallic lab. That would be even more better. It's good to read about a place, but it's even far more better to visit the place in person. If you are interested in organometallic, you should do spend some 2 3 months in organometallic chemistry laboratory. You have more experience about field. It's coming to an end. 59. So I thank all the students and everybody who joined in for today's live interactive session. I think we are coming towards an end, and hopefully we'll again meet for the third session before the end of this course. I sincerely hope that you enjoy the course and the content, and we look forward to again at the next meeting where again we can discuss more on organometallic chemistry. Till then, goodbye, thank you, and stay safe. Bye bye.